Hello, today we will present our core activity where we will explain how we obtain the necessary measures to build 6 containers in different shapes, and this we will relate it with the efficiency of using each one of the containers as a package.
The first figure we were assigned to build was a rectangular prism, and the conditions stated were that the length of the base should be twice the width, and the volume should be 2000 cubic centimeters. With that in mind, we first searched for the volume formula of the prism, which is the one shown on the right. After that, we decided how tall we wanted and used the remaining multiple to get the area of the base. We substituted with the assigned values to x, and finally we got the value of x. After that, all we did was plug in that value into our equations and calculate the final measures.
After having the measures, we move into the building of the container in a cardboard. For this, we use ruler to have the complete and accurate measures. Finally, we conclude the building process, and as it was required, we produced 2 containers. The first one, it was with all the sides, and the second one was without one base. Here are some pictures in which you can look or see which one is the one with all the sides and the other that is without one base.
Continuing, we were also assigned an hexagonal prism that had the characteristics that each side of the base should be twice the height. To obtain these measurements, we searched for the volume formula, which is the one shown on the right. After this, we substituted in the formula with the variables that represented the conditions assigned. Then we obtained the results for x and calculated the final measurements. Once we had the accurate measures, we started building our figures. The first thing we did was to use a circle as a base to make the hexagon, and then we started to build the body of the figure, and we used ruler and also some degree measures to make sure that the hexagon had the same exact measures in all of its sides. After the building process, we obtained the final results, which are shown on the images. On the right, we have the product without one base, and on the left there is the image of the container with all of its sides. Finally, we were assigned to do a cone with a radius of twice the length of the height. For this, we had to investigate the formula of the volume and replace all the values with the conditions we were assigned. After this, we cleared out for x and plugged all the values to get our final measurements. Already with our accurate measures, we started constructing our containers. For this specific figure, we had to calculate the generics of the cone. To obtain it, we used the formula of square root of the square of the radius plus the square of the height. As well, we had to calculate the needed angle to build the body of the cone by following these steps. First, we multiplied times 2 the generatrix, and then we also multiplied by pi. Then we calculated on a scale of 360 by a rule of 3. After that, we obtained that our angle was 109. With all of this in mind, we proceeded to the making of the figure. After concluding the process of building, we obtained the following results. On the right, we can see the cone with the base, and on the left, the cone without a base. In this table, we can see all the condensed information about the previously mentioned containers. Now, and as shown in the table, we will explain how we obtain the areas of each container. By calculating the area, we can establish a close relation between areas and the material needed, which is directly related to the cost of production and effectiveness of a package. For the rectangular prism, we first calculated individual areas of each rectangle that conforms the prism, and then we add them. We use the base times height formula. Lastly, for the second rectangular prism, we only subtracted the area of one base to the result previously obtained. Next, we calculated the total area of the hexagonal prism. To achieve this, we used the area formula for the hexagon and multiplied it by 2, since there are 2 hexagons. Then, we calculated the areas of the rectangles that conform the body of the prism and summed them all together. After that, for the second hexagonal prism, we subtracted the value we obtained previously for one base to the result of the area of the whole figure. To calculate the area of the cone, we search for the specific formula, which is pi times the radio times the generatrix plus pi times the square radio. We substituted all the needed values previously obtained and then calculated the final result. For the last figure, we calculated the area of the circle base by using pi times the square radio and subtracted that value from the result obtained in the last calculations. After finishing all the figures, we arrived to the following final reflections, responding to certain specific questions. The first one is which of your boxes require the least material to be built? The hexagonal prism was the figure that required the least material to be built, due to the fact that the body of the figure is constructed by a set of continuous pieces that are assembled, and its simple shape and structure facilitates the assembling, needing less unit material. We prove this by adding the area of each piece with the measures obtained, and in that calculation we obtained that the sum of all the areas was equal to 1152.59 square centimeters, which can be taken into account as the quantity of material needed. We made the same approximated calculations with the cone, which we believe could be one of the options that needed the less material. And by calculating the total area of the figure, we obtained that it was equal to 1625.31 centimeters square. On the other hand, the cone without its base was the figure that required the least material to be built, having an area of 857.82 square centimeters. The next question was, what is the relation of this with the cost of producing and using the box as a container for a new product? When evaluating and deciding which type of package is needed for a product, it is really important to consider the cost it will imply, since it has to be affordable for the type of market you have, but at the same time it has to be functional. In that sense, there has to be a balance between the cost, the functionality, and the experience it creates for the client. After building all the containers, we have concluded that the main relation between the cost and the shapes assigned is that in some of the containers the materials used were considerably more than in others, and there were some variations in the volume they could contain. For that reason, the shape of the box of the container is directly related to the monetary implications it will bring when producing the package. Our next question is, which shape of all in geometry do you think is the best in surface area versus volume ratio? We consider that the best geometrical shape in terms of relation between area and volume is the rectangular prism. It allows an accurate calculation, and since it does not have a complex shape, the volume maintains integer. As well, it allows the cost of production to be reduced by the optimization of space and the reduction of material needed. Along with these facts, we consider that it is also really important to consider the proportions of the figure, how symmetrically accurate and proportionate it is. Finally, we have our last question. How can you guarantee that the box you choose to use as the container of this new product is the best one, the one with the least cost? In order to guarantee the best decision of container for a product, we believe you have to consider three main aspects. First, relation cost efficiency. You have to calculate the total material needed to produce the package and then obtain the total cost of it. This can be done by using the areas of each side of the container, adding them, and then multiplying by the cost of each square meter. The target market. This is very important to consider since the shape of the product can be perceived differently from age to age. To set an example, we can observe that for little kids, the more rare the package is, the more they will feel attracted to it. But on the other hand, adults will seek for the efficiency and the obtainment of the complete quantity of product. The type of product also is really important, whether it's liquid, solid, or a gas. It is really important to analyze and define which container is the best, considering all the benefits and downsides depending on the type of product it is sold. This is all of our core activity. Thank you for listening, and we hope that you enjoy it.